For the everyday missions performed by Army aviators, success depends on the mechanics who keep the aircraft in top condition. The aviator must be able to depend on every part of his aircraft to function properly. For example, the aviator must have dependable and accurate instruments to fly his mission successfully. Flight instruments give him vital information: his altitude, heading, airspeed. In fact, everything he must know to fly from one point to another. Whenever the aviator can't see the ground, he's completely dependent upon instruments. In instrument flight, he determines his route with his airway charts and his flight instruments. The instruments must function properly. Remember, on top of an overcast, there aren't any road signs to mark the route. These 6 instruments are the ones which are normally found in Army aircraft. They're used in fixed-wing aircraft as well as many helicopters. The 6 instruments are divided into 2 groups: the pitot-static instruments and the gyro-vacuum instruments. These 2 names, as we shall see, come from the method of operation of the instruments. The pitot-static instruments are air-operated. 2 kinds of air pressure are required: pitot pressure and static pressure. What is pitot pressure? How is it obtained? Pitot pressure is obtained from a pitot tube, a simple device named for its inventor, Henri Pitot, a Frenchman. The pitot-static tube is usually located in the leading edge of the left wing. The pitot tube is pointed in the direction of flight. It collects the air, which is rammed into this opening at the nose of the tube. The amount of air rammed in depends on how fast the aircraft is moving. To give a true reading, the pitot-static tube must always be located where the flow of air is least disturbed. Let's take a closer look at the pitot-static tube and see how it operates. Inside the pitot tube, there are baffles in the air passage. They break up the flow of air and help extract dirt and moisture from it. The dirt and moisture are drained from the tube through drain holes. To prevent the moisture from freezing and blocking the tube, heaters are provided. They're controlled by a switch in the cockpit. From the pitot-static tube, the air is carried through metal tubing to the airspeed indicator. So far, we've learned that pitot pressure is ram air, or air under pressure, corresponding to the speed of the aircraft moving through the air. What is static pressure? How is it obtained? Static pressure enters the tube through holes in the top and bottom. Since the static holes are at right angles to airflow, air is not forced or rammed in. Static pressure is ordinary atmospheric air pressure. It does not vary with the speed of the aircraft. As we know, pitot pressure is used only in the airspeed indicator. But static pressure is used in all 3 of the pitot-static instruments. There is another means of obtaining static pressure, which is commonly used on Army aircraft. A pitot tube, rather than a combination pitot-static tube, is used. Static pressure for the instruments is obtained through tubing running to static ports on the fuselage of the aircraft. On the actual aircraft, the static ports are located where air will not be forced into them. A grid with small holes covers the port to help prevent small objects like bugs or dirt from from entering. Be careful not to plug these holes when you're cleaning or waxing an aircraft. Now we know that pitot pressure is air forced into the system by movement of the aircraft through the air, and static pressure is air at atmospheric pressure. Later we'll see that atmospheric or static pressure also varies during the course of a flight. There are 3 pitot-static instruments commonly used in Army aircraft. First, we will examine the airspeed indicator and learn about its working principle. The airspeed indicator is housed in an airtight case. As we learned earlier, both pitot and static pressure are used. The static pressure line simply attaches to the case so that the interior of the case is vented to the outside atmosphere. The pitot line enters the case where it terminates in a hollow, flexible diaphragm. Let's take a closer look at the diaphragm. By cutting away a section, we can see that it is made of 2 thin metal dish shapes joined at their edges. The corrugations on the walls make the diaphragm quite flexible. As the aircraft moves, pitot air is forced into the diaphragm, causing it to expand in size. As the aircraft increases or decreases its speed, the diaphragm expands or contracts. This movement is transmitted to a mechanical linkage consisting of gears and levers. Here we see a simplified version of this linkage. When the airspeed is increased, the diaphragm expands, moving the linkage, which in turn moves the pointer to indicate the increase in airspeed. As it contracts, a lower speed is indicated. Actually, since there is pitot pressure in the diaphragm and static pressure in the sealed case, we can say that airspeed is measured by comparing the difference between pitot pressure and static pressure. The airspeed indicator uses both pitot and static pressure. But the altimeter and rate of climb indicator use only static pressure. Before we can study the working principles of these instruments, we must know why static pressure varies during the course of a flight. First, let's clear up our terms. Static pressure is the same as atmospheric pressure or barometric pressure. All 3 mean the same thing, the pressure exerted by the air making up the Earth's atmosphere. Why does air exert pressure? The answer is simple. Air has weight. Supposing that the Earth at sea level is divided into many square inches. Let us take one of these square inches as an example. Resting upon this square inch, imagine 1 cubic inch of air which weighs very little. But take a column of air extending upward to the limits of our atmosphere. This column exerts a pressure of 14.7 pounds. This is what is meant by the statement, standard atmospheric pressure is 14.7 pounds per square inch at sea level. Therefore, atmospheric pressure decreases the higher you go. You may also refer to static pressure like this. Standard barometric pressure is 29.92 inches of mercury at sea level. Hg is the chemical symbol for mercury. When atmospheric pressure is stated in inches of mercury, the reading is always a barometric measurement. The reason for using the term inches of mercury is because the first barometer invented used mercury as an indicator. Here is a simple explanation of how this barometer operates. A glass tube, 36 inches long, open at one end and sealed on the other, is filled with mercury. This is inverted and placed in a partially filled beaker, also containing mercury. The mercury in the tube will flow into the beaker until the amount of mercury remaining in the tube exerts a pressure at the bottom of the tube equivalent to atmospheric pressure, or 14.7 pounds per square inch. If we now measure the mercury remaining in the tube, it would be 29.92 inches. This is what is meant by the term inches of mercury, and we can see that 29.92 inches of mercury is the same thing as 14.7 psi. Now let us demonstrate why static pressure changes during a flight. Here is our barometer, reading 29.92 inches at sea level. As the barometer ascends to a higher altitude, the mercury falls in the tube. Why? The atmospheric pressure has decreased above the barometer to support the mercury in the tube. As the barometer descends to a lower altitude, more air presses down and the mercury rises. As the barometer ascends to a higher altitude, less air presses down and the mercury falls. The mercury barometer is still used. However, there is another type which is much more compact, the aneroid barometer. This is the heart of this modern barometer, a special flexible diaphragm called an aneroid. It is similar to the flexible diaphragm, but has no tubing connected to it. When manufactured, the aneroid is sealed with air at a pressure of 29.92 inches of mercury, standard sea level pressure. Notice that at sea level, the walls are flat. However, if the aneroid ascends to a higher altitude, its walls expand. This happens because there is sea level pressure inside the aneroid and less than sea level pressure outside it. At lower altitudes, the aneroid contracts. At higher altitudes, it expands. In an aneroid barometer, this contracting and expanding operates a pointer on a dial. The dial reads in inches of mercury. If we change the numbers on the dial to feet of altitude, we have an altimeter. Aircraft altimeters contain aneroids and are exactly the same in working principle as aneroid barometers, with one exception. On the altimeter, there are 3 dial pointers. The short pointer indicates tens of thousands of feet, the medium pointer indicates thousands of feet, and the long pointer indicates hundreds of feet. For example, this altimeter reads 130 feet. To sum up, the case is vented to the static pressure line to allow atmospheric pressure to enter. Inside the case are 1 or more aneroids. As static pressure rises or falls, they swell or shrink. The aneroid's movement is transmitted by a mechanical linkage to the 3 pointers on the dial. The altimeter has one more feature which we will cover briefly. Turning this knob changes the number, seen through this opening, to the current barometer reading, corrected to sea level. This adjusts the altimeter to local atmospheric conditions. Here's how it's done. To adjust the altimeter, first call the tower and obtain the current barometric reading. This setting changes from hour to hour as weather conditions change. Turn the setting knob until the current reading appears in the opening. At the same time, the dial pointers will move, in this case to read 420 feet. An accurate altimeter will show the actual altitude of your location. Airfield altitude is always prominently displayed on every airfield. Now we will move on to the third pitot static instrument, the rate of climb indicator. This instrument is also called the vertical velocity indicator. This name is more accurate because the instrument does measure the rate or velocity of vertical movement, both climbs and descents, but we'll use the more common name, the rate of climb indicator. This instrument is calibrated in feet per minute. When the pointer moves down, the aviator knows he's descending, and he can tell how many feet he's descending each minute. The pointer also indicates climbing and shows the rate of climb in feet per minute. The working principle is quite simple. A static pressure line is connected to a case that is completely airtight. Connected to this line is a sealed, flexible diaphragm. At the end of the static pressure line is a calibrated leak. This leak is merely a tiny hole drilled to a very precise size. Here's how the mechanism works. When the aircraft is in level flight, the pressure in the diaphragm and in the case are equal. As the aircraft descends and encounters air of higher atmospheric pressure, static pressure increases and rushes freely into the diaphragm. It also enters the case slowly through the calibrated leak. Since there is more pressure in the diaphragm than in the case, the flexible diaphragm expands. This movement is carried by mechanical linkage to the pointer, which indicates the rate of descent. As the aircraft levels off, air continues to bleed into the case through the calibrated leak. It takes several seconds for case pressure and diaphragm pressure to equalize so that the diaphragm returns to normal. The pointer returns to zero after this normal built-in time lag. The opposite action occurs when the aircraft climbs and atmospheric pressure decreases. Air pressure rushes freely out of the diaphragm, but the calibrated leak slows the escape of air from the case. There is more pressure in the case than in the diaphragm, and the diaphragm contracts. The mechanical linkage moves the pointer to show the rate of climb. As long as the aircraft continues to climb, the pointer will indicate a climb, because the calibrated leak will not allow the pressure in the case to equalize with the pressure in the diaphragm. The rate of climb indicator shows vertical velocity by comparing the difference between the pressure in its case and in its diaphragm. The altimeter measures the atmospheric pressure as the aneroid containing sea level pressure contracts or expands, and the airspeed indicator measures the pressure of impact air flowing into the pitot tube to indicate airspeed. These are the three pitot static instruments commonly used in Army aircraft. Now we will turn to the three gyro vacuum instruments, first determining the meaning of gyro vacuum. A gyroscope, or gyro, is essentially a perfectly balanced wheel on a double-ended axle. The wheel and axle are supported by two rings which are joined together and mounted in another ring. Here is how it works. When the wheel spins, the gyro becomes rigid. By rigid we mean when the outer ring is moved, the gyro does not move. Its high rate of rotation causes it to remain fixed in its original position. This gyroscopic rigidity is used in all three of the gyro vacuum instruments. We shall learn why they are called gyro vacuum instruments as we study the working principle of the directional indicator. The directional indicator is not a compass.